Good morning, everyone. Happy Monday. We are going to conclude Unit 6 today and start on Unit 7. So if you want to navigate over to our Polylearn page and download the Unit 7 handout set, that would be a good idea because we're going to start into it today. Before we do any of that, can I answer any questions from the crowd before we get into lecture? The crowd is silent. Okay. So let's switch over to the all-knowing PowerPoint. And what did we do last time? We, excuse me, we talked about PID control. That was kind of fun. Something you actually might have heard of before this course. The idea behind PID was that it's a natural extension of this idea of S-plane design, is that adding zeros into the left half plane can attract your closed loop poles and make your system faster. Also, adding an integrator tends to increase the system type number and combat errors due to disturbances. So there's the 20-second version of why PID controllers are good. They're not so good because they're actually kind of tricky to actually design. With 3 degrees of freedom, there's a lot of balls in the air. So we had the Ziegler-Nichols heuristic to try and inform how to design the 3 gains. Okay, to conclude our discussion of S-plane design, I think it's about time that we talk about closed loop zeros. Right, this is week 7 of 9, and so far it's been poles, 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 poles. All this talk about poles, hardly any talk about zeros, so I think it's about time we get started on that. So the question that I'd first like to ask is, where do closed loop zeros come from? You might first think that every open loop zero is a closed loop zero, and that's actually not true, but it's a good intuition. So let's check it out. So I've got kind of a generic feedback loop here. I'm calling G the forward path transfer function and H the feedback path. And then I'm being a little bit more specific. I'm breaking up G and H into a numerator and a denominator, respectively. So back in week 1, we learned that we can reduce this transfer function with forward over 1 plus forward times feedback. And if we want to clear the fractions, then, or the fractions within fractions, I should say, then I want to multiply by that product on top and bottom. And doing so will make that product appear here. And the dg will cancel in the numerator, but the dh has no one to cancel with. And so the point of this slide is to get you to see that the closed loop zeros come from one of 2 places. Either the zeros of G or the poles of H. And I think that that's, parentheses surprising here, that your closed loop zeros can either be found by reading off the zeros of that polynomial or by finding the roots of that polynomial. Okay, so I guess it's not terribly surprising that because H appears in the bottom, then the bottom of the bottom becomes a top. Like if that is how you want to think about it, that's fine. But just so you know that if you have a polynomial in the numerator of your G or a polynomial in the denominator of your H, you will have a closed loop zero. Any questions on that? So now I think the next logical question is, if we know where they come from, what do they do? What do they do for us? What do they do? Do they act for us? Do they act against us? What's the implication here? So I'm going to go through a fair bit of math here, but I hope it's actually nothing you haven't seen before. If we can write the closed loop transfer function as the ratio of 2 polynomials, and just for convenience sake, I am going to restrict us to strictly proper closed loop transfer functions. Then I can factor both of those polynomials. I can factor the top into the roots of the numerator polynomial, which I'm going to call the z's, and I can factor the bottom into the roots of the denominator polynomial, which I call the p's. Now, just so you know that each of these, so zi, could be complex, just like pj could be complex. Okay, so I'm not claiming that I can always factor them into real roots, but I can always factor them into at least complex roots. And then if you like, we're also normalizing by the leading coefficient out here. So I think we're dividing out by k would be bm over an or something like that. Okay, and then I wanted to introduce you to this notation. This line and this line are the exact same. But what I'm doing is I'm using this capital pi symbol in the same way that one would use the capital sigma symbol for a sum. I'm using the capital pi symbol for a product. So all this means is take these things and multiply them together, incrementing I each time. Okay, and same story on the bottom. So this is literally s plus p1 times s plus p2 dot 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 s plus pn. Okay, just the same way that you would break up a sum as, you know, the first thing a sub 1 plus a sub 2, etc. The sigma is for sums, the pi is for products. That's how I like to remember it. Okay, so each of these z's is a closed loop 0, or at least the negative of one. So this is the negative, the opposite, negative of a closed loop 0. Right, because we're talking about factoring the closed loop transfer function. So we're kind of out of the realm of open loop poles and zeros, and we're into the, some would say, more natural realm of closed loop poles and zeros. And so the question is, if you have one or more closed loop 0, how does that change the step response? Well, we know that we can write the step response of the system if we were to take, sorry, let me go back here for a second. If we were to take R of S and we were to let R of S equal this representation of a step in the S domain, then we could multiply it over. And then we'd have a big old messy fraction on the right, but we'd have Y sub step on the left. Okay, this is exactly what you learned in your 228 Laplace analysis. And so that's what I have here, except that I've taken the messy fraction and I've expanded it out. So this is after partial fraction decomposition. Right, I have expanded, or I've decomposed the single large fraction into many smaller fractions. And I know that if I had n poles, n closed loop poles, then I will have n partial fractions. If I have n partial fractions, then I will have n residues. So again, the technical term for these numerators are residues. And we say that R sub j is the residue of the jth pole. So typically we associate a residue with each pole. And I'm making one other assumption here. It's not entirely obvious, but I am assuming no repeated poles. What we're about to learn here actually still works if there are repeated poles, but the math goes from messy to really messy. So I think that we can just do it with the simple case, and maybe you can take my word, or you can work it out for yourself that it still works if we had repeated roots. Okay, so then to get from this step, again, this is 228, but without any numbers, we can take the inverse Laplace of the top, and we get the bottom, which is the time domain representation. All of these poles, S plus Pj, turn into modes of the form e to the minus Pj times t, where I'll remind you, we can still have complex p sub j's. Okay. This would turn into a real valued system, provided you could use the Euler's formula to take these e to the complex things, and they would always appear in complex conjugates if your coefficients of your transfer function were real. So don't think that this is some crazy weird complex valued function. This is just a real valued step response with some complex things inside of it. Okay, so how do closed loop zeros come into play here? Well, actually, I think that's a good question for the class. What things in this line are affected by closed loop zeros? So what is affected, effected? What changes with closed loop zeros in this line?
Is it the residue?
Yeah, which one?
RJ, I guess?
Yeah, all of the RJs. In fact, also even the R0. That's exactly right. It's all of the residues will change if I were to pick up a closed loop zero and I were to move it over somewhere else. What's important in that statement, and I thank you for venturing that, is that the P's don't change, right? If I pick up a closed loop zero and I move it, I'm not changing any of the closed loop poles, so the P's don't change, the exponentials don't change, the T variable doesn't change. The only thing that can change are the residues, and in fact, all of them will change. And so that's the key to the analysis that we're about to do here. And I put this little sentence at the bottom because this is really the motivating factor about why we care about closed loop zeros. And that is, up to now, the effect of the nth pole, we've said, has been small if P sub L is larger than P sub J. Okay, so maybe that didn't sit well with you the first time we did it, or the first time we saw it, but if I've got two of these terms, and I'm just going to take two of them, because if I can compare two, then I can, repeat that exercise for the rest. And one of the terms has a time constant like this, say. And the other has maybe even a really large initial value, but it has a super quick time constant. We have said that blue will dominate red. So we say that the blue pole dominates red because the time constant, so time constant on blue, is larger than time constant on red. Okay, maybe I didn't pick the right two functions here to plot for you, so if you'll permit me, I'll redo them real quick. So let's take something much slower and compare it with something pretty fast. Okay, so if I add, so remember I'm adding all of these terms together, and so what I'm plotting here is, say, r sub red times e to the minus pole red times t, and r sub blue times e to the minus pole sub blue times t. So I'm just taking two of these terms, adding them together, and if we look anywhere past here, all we see is blue, pretty much. And that effect, this, if you're not comfortable with ignoring this region, well, just increase the time constant, or sorry, decrease the time constant on red. Maybe pick something that looks like that. Now, all of a sudden, the region of time that we can ignore red has shrunk. Or sorry, the region of time where red is effective has shrunk. So the region of time that we can ignore red has grown. This is an illustration of the dominant pole approximation. And what I'd like to say now is there is another way that we can make these simplifying assumptions. So let's take two of these terms and let's give them identical time constants. But in the second one, we start much smaller. Okay, so tell me, in this diagram, this is in the time domain, in this diagram, which of these two, blue or red, would dominate the response?
Blue.
For sure, it's the bigger one. So what controls whether a term, if two terms have nearly the same time constant, what controls their initial amplitude?
The zero.
The residue.
Or the residues.
The residue, which are affected by the zeros. I think that's where you're going. So you
Yes.
were already ahead of me. Exactly. So this would be residue sub blue, and this would be residue sub red. And so what I think that we're getting at here is that for two poles that have comparable time constants, that is, two poles that we could not before make a dominant pole approximation for, because they both decay at the same rate, because their real parts are roughly equivalent. If we have two of those poles, maybe we can ignore one of them if their residue is small relative to each other. Okay, so that's a lot of what this, a lot of the subtext of this class is: systems are complicated, second order systems are manageable. Can I make my system into a second order system? Like, that's one of the subtexts of this class. And this is, I'm about to get to one of the ways that you might be able to make that assumption. So if I can show that one residue is much smaller than the rest, then I could make an argument saying that the effect of that pole is small. Let's toss it out. Okay, that's the motivation. That's where we're going here. So the question now is, what things about the transfer function would make one residue smaller than the rest? And to answer that, we're basically going to do the cover-up method, but with no numbers. Okay, so back here, this is what we originally said. So this is the step response before partial fractions. Is there a question?
Yeah,
I saw a notification come up. Connor, go for it.
Yeah, I was going to ask you really quick. In the S domain, do the residues, can they contain values of S, or are they just numbers?
They are just constants.
Okay.
So maybe what you're thinking is sometimes we had stuff like S squared plus 3S plus 8, and we would put a CS plus D up here. Is that maybe what you're thinking?
Yeah. Mm-hmm.
So yeah, the way I've gotten around this is the fact that I've written all of the denominators as first order. The price I pay for that is that the p's can be complex, whereas here everything was real. But yeah, as long as you write the denominator as first order, then the numerator, the residue, will be 0th order, or a constant.
Oh, okay.
So yeah, I'm not saying that this would be the most convenient way to do partial fraction expansion, but it is mathematically more compact to write it like this. Okay, so the thing on the left is the step response. I know it's a step response because the step S is hanging out down there. This is before partial fraction decomp, and on the right is after partial fraction decomp. And the idea is, behind partial fraction decomposition, is that these two things have to be the same. Okay, so one way to view the cover-up method is pick the residue that you'd like to solve for, in this case A sub L, multiply through by S plus P sub L. Right, so that S plus P sub L appears everywhere. I'm multiplying both sides of the equal sign by the same thing, which means I still get equality. And what can we do here? Well, in the denominator here, there will be, one of these terms will be S plus P sub L. And so we'll get cancellation with that. So that's why I'm excluding L from this product in the next line. No cancellation here, so that S plus P sub L just hangs out. And actually I can say the same thing over here. There will be n terms. One of those terms will be the lth term. So what I'm doing is I'm splitting out the lth term out here, and then I'm skipping the lth term in the rest of the sum. Okay, so I think, what would you do next if you were going to do partial fractions now, after you've done the cover up? I mean, the very next step is evaluate it at the pole location. Right, so then we do on both sides, evaluate this at S equals negative P sub L, and evaluate this at S equals negative P sub L. Okay, and that's exactly what we got on the next slide. So let me show you how we go from 15 to 16 here. If I evaluate the left at S equals negative P sub L, then all the S's get written as negative P sub L. That's not news to anyone. What is news is that there's no cancellation anymore because we have canceled the S plus P sub L factor out of here. Now what happens on the right is the same thing. We plug in negative P sub L here, which makes this whole thing go to 0. We plug in negative P sub L here, which makes all of these things go to 0. So what we're left with on the right-hand side is the residue that we want. Okay, I mean, this is the quote-unquote proof of why the cover-up method works. And so this is the expression for the lth residue, or the residue due to the lth pole. And so now I think we're available to answer the question, what makes A sub L, let's say in magnitude, let's make some magnitude of A sub L small. Relative to the others, relative to other residues. What do you think here?
I'm just gonna throw it out there. What about making the denominator bigger compared to the numerator?
Sure, if the denominator were to get really, really big, then this thing would get very, very small. I absolutely agree with you. How would the denominator get big? Well, if the lth pole was large. So actually that's itself interesting, is that if we were to move the lth pole very, very far away from the origin, then absent any zeros in the system, that would make its residue small. But remember, the theme here on this sub-lecture is about closed-loop zeros. And so I'd like for us to focus up here. Because remember, this is the ith closed-loop zero. And this is the lth closed-loop pole, or it's the pole whose residue we are looking at here. If the denominator were to get big, then this fraction gets small. If the numerator were to get small, the fraction gets small. So what makes the numerator small?
If all the zeros got closer to PL.
Is it all, or is it some?
Oh, actually, you only need one to equal PL.
There you go.
So multiplying them together.
Bingo. If any of these factors, right, we're not adding, this is a product. If any of these factors get close to 0, then the product, then the product gets close to 0, all right? Assuming the others are all relatively finite. Okay, so if P sub L gets close to any Z sub I, then the numerator goes to 0. Or gets small, if you like. Which means that the residue gets small. Okay, so here we have the answer, finally. What is the effect of closed loop zeros? Well, what is one effect of closed loop zeros? That is, if any of your poles, closed loop poles, are close to any of your closed loop zeros, their residues are small. Their effect on the step response is small. It'd be really nice if I could see your reaction to that, because that's the payoff. That's the point of this. If I have a system, a closed loop system, with a closed loop pole here, closed loop 0 there, and a closed loop pole way the hell out here. So these are all closed loop pictures. On the one hand, so I'm jumping straight into the hard question here. On the one hand, this looks like it could be a candidate for the dominant pole approximation, right? This is a large psi. On the other hand, this is a very small distance. So this is a small residue, a sub 1, say. So this is two competing factors. The large psi says that this pole should dominate. The small residue says that this one should dominate. Okay, so I want to just call your attention to the fact that closed loop zeros can help us ignore some closed loop poles, but also in this situation they confound with things that we already thought we knew. Is that I think what I was trying to teach you earlier was that poles closer to the origin tend to dominate poles that are further away. That statement is true in the absence of zeros. In the presence of zeros, things get more complicated, which is why we've put it off until now. So let's take an easier case. If I've got a closed loop pole there, a closed loop pole there, and a closed loop 0 there, then clearly everything points to this one dominating. Right, both the psi ratio, domination by psi, but also domination by residues as well. Not by, but via. Connor, go ahead.
Does that dominant range apply to pole zeros or just pole?
What's a pole 0?
Combination?
I don't understand.
The psi range, the 10 units on the real axis for dominance, does that apply with just pole to pole, or is that pole to 0 as well?
I think, okay, now I see. Yeah, it's just pole to other pole. Yeah, so psi is a ratio between the time constants in psi is a ratio of these things.
Okay.
And the time constants of all these residues, the time constants of all these modes depend exclusively on the poles. They are not affected by the zeros. And so it doesn't really make sense to compare the real part of a pole to the real part of a 0.
Mm-hmm.
Yeah, because what we're trying to do here is comparing time constant of pole 1 versus pole 2. And the zeros don't enter into that.
Okay.
Yeah. Thanks for clarifying that for me. Was there a chat? There is a chat. What is the cent symbol? Uh-oh, I see no cent symbols.
It's the complex number symbol.
Ah, okay. Has that been on the chat for that long?
No, it just must be.
Okay. This means the set of all complex numbers. You know, this is the set of all real numbers. This is the set of all integers. This is the set of all natural numbers. you know, math people like these double-stroked symbols to mean the common fields. Cool. Nice work. Are there any other questions on this before we start the next unit? You're welcome.
So in general, with the first pole zero plane example you drew, is what we assumed before, where if it's farther away from the origin, it's more dominant or it's less dominating.
Yep.
Is that still true, or did we just kind of specify it more?
It's still true if you have no zeros.
Okay.
It's the fact that the two time constants are, one time constant is smaller than the other, like that is also still true. But what has happened in this particular case that we've got here on the screen is, so let's give ourselves some numbers here. So let's call this pole 1 and pole 2. So if I were to look at the step response of this system, then pole 1 would have a mode that decayed very slowly. So this is a slowly decaying mode, but its residue is very small. So we'd have something that looked like that. And let's see if I can do another color here. This pole has a very fast decaying mode, but its residue would be larger. Okay, so this is why I don't think that either one of these would dominate the other, is because in the region where you'd want domination to happen, they're both kind of comparable. And in the region where you can't really expect domination to occur, it's actually quite wide, because this one starts small but doesn't decay very fast, and this one starts big but decays relatively more quickly. Is that these, I can't look at this graph and say, oh, orange is more important than blue, because orange is bigger than blue here but smaller than blue there.
I see. All right. Thank you. Thank you.
Yeah, sure thing.
I had another question.
Go for it.
So if there are a complex pair of poles and a zero is like between them, like right on they both have the real value similar. So like the zero would be right on the real axis, in between the two poles. Does this also hold?
So what is this in that sentence?
It would make the I guess magnitude of the residue or small, because
but these two complex conjugate poles, so call this has residue 1, this has residue 2, because they're complex conjugate, their residues are complex conjugates, which means the magnitudes are the same. Whether they're big or small, they're the same number. So like moving this 0 there or there, these two will always have the same magnitude. Is that, did I break something?
The 0 were squared, like there's 2 of them on the same spot. Are you saying that since there's 2 complex conjugate poles that they kind of are stronger than the 1, 0, or are you saying that this is something different because they're complex conjugate?
I think the original question was, if we have complex conjugate poles, does the placement of a 0 make one of them stronger than the other? Jared, is that accurate?
No, I was just wondering if it had an effect on the dominant. So let's say there's a pole way out to the left.
Okay, a third pole. And now you're asking about a 0 here.
Yeah, how will the 0 affect which pole is dominant, or which poles are dominant?
Good. So this picture that I have up here on the left, in my mind, is very similar to the original picture that we had on the previous slide. It has a fast pole out here and slow poles back here. However, these residues will be smaller. So we have the same kind of tension that the two things we've just learned about are competing. And so this is a difficult case to say just visually which one will win.
Will it have less an effect because there's 2 poles versus 1 0?
No. Well, I mean, the more zeros you were to put here, then yeah, the smaller these residues would become. Because we get things like, in the numerator of this fraction, right, we'd have lots of things close to 0. And so everything would multiply together, and so we get that compounding. So yeah, you can place multiple zeros here. I mean, if you physically can do that to minimize the effect of these poles. And I mean, that's a valid design technique, is if somehow you can't drag the poles any faster, but you are magically able to insert zeros close to them, that's legit. Like, what would happen if you were able to insert a 0 here and there? Well, this is the ultimate in small residues. This is a 0 residue, if you think about it.
So would the opposite be true for poles? Could you add more poles to increase the effect? And I don't know why you would, but slow this down.
That's a really strange question. Like, strange in that I've never thought of it before. Basically, I'm always looking for ways to simplify systems, and injecting more poles would only serve to complicate things. I guess that's an excuse as to why I haven't thought about it before. I can't tell you right now whether injecting more poles here would diminish the residues of these poles. I can think about that, but I'll have to get back to you.
No, I that is helpful, but I also meant over on top of the other poles, on top of the other complex conjugates.
So here's our starter system. And sorry, can you run me through one more time what you'd like?
So if there's a 0 on the axis at the same location as the complex conjugate poles, and you on top of that say you've got a double complex conjugate, does that doubling of those poles increase or slow down the system? Does it decrease the effect of the 0 that is there, I guess?
Yes, it would. I can confidently say that. Yeah, so this system versus this system? I don't know. That's, I guess I'm less confident now. If I'm comparing this system to that system, I'm not quite sure. Yeah, so this would be somehow like if you were granted a magic black box that gave you a 0, but you had to pay for it with extra poles, would you want to make that trade? And I'd have to analyze it. I can't say off the top of my head.
Okay.
Yeah.
Thank you.
Sure. Okay, people, we got to move on. But that was a good closing. So I'm glad we got through that.